Hello, everybody.
Wait, no, not yet.
Not yet.
Okay. You can go.
Hello, everybody. Prague Seminar for Mathematical Physics is back again. And today it's my great pleasure that I can welcome our speaker, Thanassis Chatzistavrakidis. I hope it's correct. He's a researcher from the Ruder Institute in Zagreb, and he came to us with a very exciting talk, I guess, because of the title. It's a basic curvature and Atiyah cocycle in a possibly higher gauge theory. So it's my personal love, I must say, which give me the clue that Atiyah theory is not abundant at all in the community of physicists. So I think it will be a good experience, not only for me, but for all of us. Thank you.
Thank you for the kind introduction, and thank you all for being here, for having me at your seminar. And it's always nice, of course, to be in Prague and also give a talk in front of so many experts. So I want to discuss with you about two objects that I came to like a lot. It's the basic curvature and the Atiyah cocycle. So both of them are measures of some compatibility between some connection and some structure. In the first case of the basic curvature is between a connection on some algebroid and the compatibility of this connection with the bracket on the algebroid. In the second case of the Atiyah cocycle, it's about connections on differential graded manifolds and the compatibility of them with the homological vector field on them. And since I'm a physicist and not a mathematician, actually, I got interested in these structures from certain physical models that I was studying, which I will try towards the end to motivate or argue how these two objects come out naturally from physics without actually putting them in, but they actually come out. Okay. So I will try to go constructively in this direction. So I will start part one. Part one will be about connections and tensors, let's say. And let's start as follows. Let's suppose that we have two vector bundles. So one of them I will call it for the moment V, and the other I will call it E. And I will also assume that this second one has a map that anchors it to the tangent bundle over the manifold over which it is defined. So for the moment, I will not assume anything else, but shortly I will. In fact, I will even restrict the framework even more. But the question now is kind of how do we define covariant derivatives of sections of V along sections of E? Right. So this is a topic that is actually, there are many experts here in the audience. So I'm looking at what is called, I will call this E connection. I mean, it's actually, I'm going to look at E covariant derivatives, but along this misnomer. So I will be looking at objects like this, such that, so this is how I will denote these connections. So for a function goes out, and when the function is here, we have a Leibniz rule. Like this. And now, of course, it's clear why I assume the existence of this map here, because I need to make sense of this object. And to make sense of this object, what I do is that I anchor the section E, create a vector field, and act with this vector field on it. Okay, so I will call this object, which it's any connection on V. I will call it E on V, okay? So to talk some shorter words. So now, if you are lucky enough and have a, and also if you have an ordinary connection on V, so I will denote it as just nabla. If you have an ordinary, so if you have a, let's call it TM on V, right? So an ordinary connection on V, then you can actually induce a new connection via the number. So you can create a nabla E, which is nabla rho. I will denote this special connection with a bullet. This is not a generic connection, of course, right? It's a very special one. And I will be denoting it with a bullet over it always from now on. And it will be useful in the following also to define the difference between the two. Because this will, well, when we choose the induced connection, then the difference will be zero, of course. But in general, I will define this as phi EV as the difference of these two. So nabla EV minus nabla EV. Okay, so this is of course linear in both arguments. And just as a last part of notation, I will mostly now restrict my considerations. So I'm not going to consider arbitrary anchored bundles. I'm going to consider either Lie algebroids. So I will denote Lie algebroids with E, okay, and or Courant algebroids for the time being. Courant algebroids I will denote to have some extra notation by E hat here in this talk. Okay, and moreover, I will be mostly, but not exclusively, be looking at E on E's. So I will be identifying also the vector bundle V with the vector bundle E, or E hat. Okay. So this is the setting regarding connections. And now I'm going to go first and look at Lie algebroids. So this is, let's say, A. So let's go to B. I'm going to look at Lie algebroids. So I will be looking at E on E. So this is my notation for Lie algebroids. So I will have an E on E. I will denote it as a code like that. It's not necessarily the induced one. And I will also be looking at an ordinary connection, a TM on E. An ordinary connection on the Lie algebroid. So now, when you have these two objects, you can construct the following three tensors. The first one is an E torsion. So we'll be denoting it as E torsion, right? Which is a tensor that I will denote like this. So it takes two sections, and it's the usual definition of a torsion. So it's the difference between these two minus the bracket between the two. This is the Lie bracket on the Lie algebroid. So that's a reasonable torsion tensor that one can define. Of course, it agrees with the ordinary torsion tensor when the Lie algebroid is the tangent bundle. And there is also an E curvature tensor that we can define for this E connection, which you would call RE, and it would be the commutator of derivatives minus the Lie bracket here. So the usual definition. Now, that's also a good definition of a curvature tensor for an E connection, but this is not the end of the story. So there is a third interesting object, which is exactly what appears in the title. It's called the basic curvature tensor. So the basic curvature tensor has to do more with the other connection, with the TM on E. So this was defined essentially for the first time by Anthony Blaum in 2004, and it was called basic curvature, I think, for the first time by the name is Krajnic in 2012 in the study of representations of homotopy. So this object, I will denote it as SE here, takes two sections again. It's actually a vector field actually here. So X will be in TM. Okay. And it's defined as follows. So you take this connection I denoted as lambda, the TM ring, acting on the Lie bracket of the algebroid minus lambda X E prime minus E lambda X E prime. Up to here, this is not a tensor, so actually you have to do a little bit of more work. So it's minus nabla E along another vector field plus nabla E prime. So the vector field that you have to put here is one from a E connection on Tm. So we'll define right away. So this nabla bar E. So this is a E on Tm. It's kind of the opposite connection than the ordinary connection on the Lie board, right? So this nabla bar E Ex, it is the anchoring of the ordinary connection of E along covariant derivative of E along X plus the Lie bracket rho with X. So this we can check this connection. Did I write things correctly here? Yes, I did. Okay, so this is also a tensor. And so there are these three different tensors. So this is a tensor that kind of tells you about some structure on the base and some structure on the fiber, right? So it's a very interesting object. And one of my arguments basically is that in physics, or at least in the models that have been looking, the natural tensors that come up are this and this, and never this, not the curvature. So yeah.
What is the basic curvature for when we use the tangent bundle?
Yeah, let me make a couple of remarks. So let me make three remarks among many. So the first remark is that for E equals Tm, as it was asked, and let me specialize it for zero torsion, S is R. Well, actually, it's minus 1. This is stupid conventions, maybe, but I will define it with convention. So S is R, is minus R. Okay. So the two notions agree on the tangent bundle, of course, but depart when you go to anything else. So the second remark I would like to make is that, of course, you can rewrite this definition here in a kind of interesting way. So you can see that this is equal to minus nabla X of the E torsion minus some tensor, which I will call C here, plus the symmetrization, because this is symmetric, where this C is what would be almost the curvature if I had chosen. It would be the curvature if I had chosen the induced connection. So C E X E prime is commutator nabla E comma nabla X E prime minus nabla rho E X E prime plus phi of nabla X E prime. So you see that when I choose the induced connection, phi is 0, and then the rest actually gives me the curvature. Okay, which makes sense, of course, because then you would get, for example, for the tangent bundle, you would get this, so that you would get two terms which are from the algebraic identity, right? So the basic curvature is not just the covariant derivative on the E torsion, it's more than that. Okay, it kind of encodes both. The third and final remark in this context is that essentially you can use the E torsion and the basic curvature as the two independent things that define the E curvature. So the curvature, you can define it as so the R and E double prime, let's say, you can define it as minus S E prime rho E double prime plus terms with, which I'm not going to write, which involve the E torsion and the endomorphism phi. So actually, you can, this is equal to the commutator of covariant derivatives, okay, for Lie algebroids. So you can use this as a definition if you wish. So they are not independent. Now, that's the story for Lie algebroids. So now I want to go and ask the same kind of questions maybe for Courant algebroids. So suppose I have E hat on E hat. Okay? So we denote now like hat, of course, and Tm on E hat. Again, I'm denoted as nabla. Okay. So what's going on now here? So famously, if you have an E hat on E hat, if you write down, let's say T E hat, this is not a tensor, right? T E hat means this definition for E hat. Okay. So this is famously not a tensor because it does not transform linearly in all its arguments. And then there is at least one solution to this problem found by Gualtieri, which is called the Gualtieri torsion, maybe. So I will call it the E hat torsion here, which I will denote it with a calligraphic E hat, E prime, E double prime, and this is equal to the T E hat, E prime, E double prime. So now I'm working on Courant algebroids, and so I have the fiber metric, which I will denote like this, and also I will be writing now for the skew symmetric version of the structure. Of course, there is a version for everything that I will write for the Dorfman version of the structure. So what one does to correct the non-tensoriality is that you can do that. I denote sections again by E, okay? That's hopefully not a problem. There are hats here and here. No, this closes, it's this one. Okay, so this one, it's a tensorial object, and this is the Gualtieri torsion. Now, I'm going to ask the same question now for the basic curvature. So the basic curvature, if I write here S E hat, E prime, this is also not a tensor, never. So these are not tensors even for the induced connection, okay? Even if I take the induced connection, these are not tensors. Also this. So what I will do, actually there is a very interesting fix, which is completely similar to what Gualtieri did. I'm going to define a calligraphic S E hat, which will be the Courant algebroid basic curvature, E prime, E double prime, X, S, this object here, which we know that it's not a tensor yet, and then it is plus 1/2 bracket parenthesis nabla. Now recall that now we're talking about the Tm on E hat, right? Correction. So here I'm going to use double prime X E prime, right? Minus that symmetrization of this double prime double prime X E prime E. So in the same way that in the torsion case, we took the first term, right, and we put the third section here. We do say similar thing with the last two terms in the definition of the basic curvature. This object now is a tensor in all its arguments. It's actually, it encodes the like, if you think of the example of tangent plus cotangent band, the standard Courant algebroid, whatever, it encodes the curvature, the ordinary curvature, and the basic curvature, potentially of the dual Lie algebroid, if you think of this as a RBI algebroid. Okay, so now remarks here. Different limits. So remarks here. So the first remark I wanted to make is that if we choose the bullet connection, so the induced connection, then well the R E hat bullet is a tensor. Is fine. So this the E curvature is a different story than the other two objects. So the other two objects are never tensors. The E curvature is a tensor for Courant algebroids for the induced connection. Okay? So they are different, kind of. They have this fundamental difference. The second observation is that for the basic curvature of a Courant algebroid, there exists also a nice formula, which is that it is minus nabla x of the Gualtieri portion plus terms with this C, which is still a tensor. Okay, so similar terms like this one plus a couple more. And then one of the things that I don't know if we will have time to say, but I'm going to mention it now, is that exactly as, so if you start thinking about field theory, so if you construct models which have an underlying Lie algebroid structure, like for example the Poisson sigma model, I will come towards this in the end, the natural objects that appear are the E torsion and the basic curvature for a Lie algebroid. If you think about Courant sigma models, for example, the natural objects that appear there, if you try to think in target space covariant terms, are the Gualtieri torsion and this object here, this basic curvature. Okay, so this ends part one. Are there some questions maybe in part one?
Maybe I have a question. Do you have any systematic way how you find these terms which you want to have in tensorial?
Me not. I have to say that I had this formula for like 8 months now, and I've been asking around people if they have seen it before. Everybody said no, apart from somebody last week. So I should put a reference here. Thank you for asking this because I forgot. So there is a fairly recent paper, actually it was published a few days ago, but it is in the archives since 2020 by Yotes, Mehta, and Papandonis. 2020 in archive, that also has this formula as an example of a little bit of a more general way of defining this kind of structures. So yeah, you can consult this paper. I think I haven't had time even to go really deep into it because it's really last week that I learned about it. But thanks a lot for the question. So part two, we switch a little bit gears, and I'm going to the DG manifold picture because I think that there are some interesting things to learn here, even before going to discuss how these things appear in physical models. So, let's discuss a little bit about homological vector fields. Well, I guess most of the people are experts on this, but let me nevertheless mention that suppose that in the case of a Lie algebra, so this is about switching picture from the ordinary structures to structures on graded manifolds, right? So for the simplest example is the Lie algebra. So you have a Lie algebra G and a bracket. So this satisfies the Jacobi identity. But But then there is an alternative picture, which is to think of the Lie algebra in the shifted sense. So you create a very manifold which has some coordinates, let's say a. My notation, I figured is a little bit stupid, but okay, I'm denoting degree n objects with the nth order letter in the alphabet. And then unfortunately, I have indices of the same sort. So, okay, let's say that we have degree 1 coordinates A here, and then there is a vector field on this, which is minus 1/2 C A B C A B A C B over 3 A. So this is the Chevalier-Eilenberg differential. And then the Jacobi identity is Q squared equals 0, right? So which means that it's follows. So this is a simple example, and this simple example generalizes nicely to the case of Lie algebroids. So this is due to the work of Weintraub, I think 97. So in the case of Lie algebroids, where you have E, or as we denoted it, you have your bracket and you have the map to the tangent bundle. And then these satisfy, I don't know, the axioms, right? The Jacobi identity to the Lie bracket and one more axiom, which is the Leibniz rule or morphism of Rho. And then this is equivalent to thinking about the degree shifted by 1, E, with a Q. Let me write the Q. So it's the degree 1 vector field that squares to 0. So normally we would write the Q as, in general, as rho A mu A B over dx nu minus 1/2 C A B C of X. Now, in general, A B A C B over the A. So the Q squared equals 0 is the actions of the algebroid. Now, I like to write this actually in a little bit different way. But it's really the same thing. I'm not changing anything, I'm not doing a transformation or anything. I'm just rearranging terms. Okay? Because you see, if you start doing x-dependent changes, and if you start changing bases, this is not a tensor in other words. So this C is not a tensor, right? It doesn't belong to sorry. So okay, so the question is, can you present a tensor here? Just to have a feeling about the geometric quantities that play the game. And the tensor, of course, we write here is what else? It's the torsion, right? So so actually you can rewrite this nicely in a more target space, or not targets, but in a more like covariant way. Let's say as well, you have to only think about changing a little bit what the derivative that you see here is actually to something which is a covariant derivative, unlike this one. And then this will be minus. Is there no? No, it's plus for some reason. PE ABC AD D over DAA. Okay, so this is like how to present a homological vector field in terms of the torsion. Of course, like when you start thinking about the current theory that this might correspond to eventually, the homological vector field will play a role in defining the nearest operator. So eventually it will not be the nearest operator, but it will be related directly to the nearest operator. So the nearest operator will contain the torsion for Lie algebroids. In other words. Now, what I'm interested in for the moment, though, is to think a little bit in terms of this of the derived philosophy of the idea championed by a number of people, like of course, from Schwarzbach, from Grabov, or Reutenberg, that you should replace difficult structures on this side with simple structures from the other side that you know very well, like functions and vector fields and operations on them, which you know much better. So, for example, for Lie algebroids, here we can think of, if we consider a section, we can think of mapping it to something which we call iota E here. So this iota E will be a section of the tangent bundle of E1 of the great manifolds, and it will be a degree -1 object. It will be something like this. So if you map your section of E to this vector field there, then the anchor famously is equal to the Lie derivative with respect to the homological vector field Q on iota E, and the bracket of the Lie bracket on the Lie algebroid is equal to the Lie bracket of vector fields LQ iota E prime. So the difficult bracket is just the ordinary Lie bracket of vector fields. So the question here for me is, can you derive E connections, E torsions, E curvatures, basic curvatures? Can you see them as derived quantities? Instead of giving these difficult definitions, can you see them as coming from the DG picture? So to do this, you have to, I'm using this one, I suppose.
Yes.
To do this,
There's a dry one as well.
excuse me,
There is a dry eraser as
I
well.
think that's fine. So to answer this question, whether you can derive not only brackets and anchors, but whether you can derive the whole geometry associated to a connection or to an E connection, actually, you have to start thinking about studying connections on the DG manifold now. But on this side, I'm not going to discuss anything difficult, because of course you can define, DG vector bundles and DG Lie algebroids and things like that. But I don't really need all these structures. The only thing I need is just ordinary connections on the graded manifold. So what I'm going to discuss now, is there a way to put this up, the other one up, so that it's visible? Probably, right?
Yeah.
So what I'm going to discuss now are, so I will consider a DG manifold MQ, and I will consider, well, TM on TM, the simplest thing that exists, right? Ordinary connections. So I will denote this as a grave nabla, okay? A nabla of a grave. Okay, so what it is, this is something. If I will denote sections of Tm by x to y. And nabla grave x y will be my connection, and it will satisfy that something like this. So this will be nabla grave x f, well, x of f y plus -1 f x f nabla x1. So in other words, you only have to be careful with the signs, right? Because all this stuff can have degrees. The degree of nabla itself is 0. Okay, it doesn't have degree. So now what's nabla xy? Degree is x plus y. Okay, so now I have something like this. I can define torsion curvature, right? I will denote them with the grave. I'm not going to write down the definitions. The definitions are the ordinary ones with care in signs. Right? Okay, so now, so you see, previously I had 3 objects. Now I kind of have 2 objects, because like in the setting that I'm working, it doesn't make much sense to define a basic curvature because it's the same. But there is a third object here, which is interesting. So it is what is called this Atiyah cocycle. I'm taking the definition from Mehta's text non-su 2015. But I think that I'm sure it also exists in earlier papers actually. So I will denote this as at. It takes 2 vector fields on M, and it is the derivative along the homological vector field xy minus this minus this. So it kind of measures whether the two structures are compatible. Now, what is important about this object, apart from the fact that personally I ended up in this object through looking at higher gates theory, but at this stage, what is important is that, well, first of all, obviously LQ at is 0. I mean, this is what it means to be a cocycle anyway. The second thing is that this object, it would be graded symmetric had the torsion be 0, but actually the graded symmetry of, so this is not a sign. So the graded symmetric part of this is equal to LQ torsion. So actually for torsion equals 0, it is graded symmetric. And the third thing that I would like to remark is that if you take the Jacobiator of Atiyah, so Atiyah of Atiyah, this is not 0, but it is related to the nabla at. So it's something like this. I mean, this or something like that. So actually, what these people showed, and more recently what they actually proved, so in a more recent paper, Spino Su from 2021, is that there is for t equals 0, there is a something which they call the Kaplanov infinity algebra. Actually, L infinity 1 algebra, with brackets being, the first bracket being the derivative along the homological vector field, the second bracket being the Atiyah cocycle with a minus convention and stuff. So and then the the higher brackets, which I'm not going to write, they actually found a closed formula for all brackets, and the brackets depend on the Atiyah cocycle, its derivatives, the curvature, and its derivatives. So B3 actually is something like minus nabla at plus, and then it has curvature terms. Okay? So in particular, when the connection is flat, it's all the B's are derivatives of the Atiyah cocycle. Okay? And how is it related to this story, that this question we asked here? So this brings me to part C. Derived tensors. So recall, maybe I should emphasize it one more, that I work with Lie algebroids here. So there's no hat anywhere. This is Lie algebroid story. Nevertheless, this story here, I mean, you can pretty much directly write it. I mean, this has nothing to do with the Lie algebroid, it's a DG picture, so you can write it for any manifold. So now let's go back to Lie algebroids and try to answer this question. So the first we would like to see is how should we write this kind of object? So the way to actually, there is a very straightforward way to identify this with a connection here. So you take that nabla, LQ, delta E, delta hat. So let's identify these connections like this. So then it is straightforward, of course, once you have this, to write down what happens to the E torsion, right? But my interest is not, of course, to just write down the result here, which you can write because this is this minus the other minus the bracket for which I know. So you can just write something, but also to understand how this something is interpreted on the DG manifold side. And the answer to this question is the following. So this is equal to the torsion of the grave connection, LQ iota E prime, but not only that, but plus the Atiyah cocycle on first here, iota E prime. Actually, this tells us that the E torsion on a real algebroid is a derived tensor from the, if you want, from the torsion of a connection, of an ordinary connection on the DG manifold picture of the algebroid, if and only if the Atiyah cocycle in this locus of degree -1 vector fields is 0. Of course, you can see this the other way also. You can think that the E torsion is the Atiyah cocycle of this locus if the torsion is 0. Now, what about the basic curvature? The basic curvature, this is something that I didn't define from the other side anyway. But the basic curvature is actually the curvature of the connection grave along LQ, along, here I have a vector field X. Now this X comes first, LQ, iota E prime, minus curvature X, LQ, iota E prime, iota E. But once more, this is not the end of the story. There is here the nabla of Atiyah. It first comes E prime here with minus E prime, iota E. So once more, the basic curvature, we can see it as a derived tensor from the curvature. Again, it's the lead derivative of the homological vector field that does the job everywhere. But there is also this obstruction by the number of the Atiyah cocycle. You can, of course, for Lie algebroids, you can ask the question also for the E curvature, right? So the E curvature actually is not similar. The E curvature is just the curvature LQ iota E, LQ iota E prime. But it has two LQs. Right? So this. So the E curvature is also derived tensor in this sense here. Now, you can play this game for Courant algebroids also. I'm not going to do it here, but if you're interested, really, it's a bit more tricky. But if you're interested, anybody can ask me later to discuss it in detail. Okay, so this is how what the role of the Atiyah cocycle is in deriving tensors for Lie algebroids. Now, for Courant algebroids, as I said, I'm not going to do the job here, but nevertheless, I want to discuss one thing for the Courant algebroid, just for completeness. So suppose that I have the DG manifold description of a Courant algebroid, which is in terms of the degree shifted cotangent bundle of the degree shifted tangent bundle. And then here, of course, if we look at the coordinate system, we will have coordinates x mu of degree 0. Then we'll have coordinates in T1 and a mu. And then we'll have coordinates b mu of degree 2 and a mu of degree 1. So 0, 1, 2, 1. Right? I will combine these two coordinates into one object, which is a. Don't confuse it with the Lie algebroid version, but hopefully we will not. So these are the coordinates here. And then, of course, we can write down a homological vector field and then try to play this game that I played above for the Lie algebroid of writing it in terms of tensorial quantities, right? And, well, I mean, we're not going to do the whole calculation, so I'm going to write down the result directly in a covariant form. And the result is rho a mu, a 0. I'm not going to define what these are. There are some proper covariant derivatives which you can look it up. The second term is beta AC rho a mu, the mu minus the Gualtieri torsion ACAB, AAB, times some degree -1 derivative. Of course, this starts with d over dx. this starts with d over dA, right? But they are covariantized. And then there is a third term, which is minus magna rho with a degree 12 plus 1/3 the basic curvature for a Courant algebroid mu ABC, AB, AC, AA, and then a d minus 2 degree derivative that starts with d over dB. So you see that when you write in a covariant form, the homological vector field for Courant algebroid, what you see is the Gaussian torsion and the basic curvature. Good. Now, I'm going to, in the last 10-12 minutes, I'm going to go to part 3, which is about gauge theory. Do you have any questions so far here?
Maybe I have one,
Yes.
because I got stuck a bit with covariantization already for the algebroid, actually. If you go back and set the tensor to 0, the torsion tensor over there, you don't get back the formula. So your Chevalier-Allen differential becomes 0 immediately.
I'm not sure I
The
understand.
torsion is 0. In
The E torsion is 0.
Yes. So you just have the first term then. And you have to show that that's an important by itself.
Yeah, I'm not sure you can do that.
So, but so maybe wait. In fact, I'm just confused. Do you get back the non-covariant case at some point? I'm
And
confused
these two
about.
lines are equal. I haven't done anything. They are just equal, right?
Okay, they are equal. Okay.
Yeah. Yeah, it's nothing. I'm not doing
And I
anything
thought
deep.
that the.
I'm not doing anything deep. It's.
Okay.
I'm just rewriting things in a covariant way. Because I have a reason to do that, which I will explain now in the gauge theory. Let me erase the other one because this is more recent. So what these funny tensors can do for me? So part 3. Gauge theory. Of course, I don't want to be too general here, and I don't want to go into too many details. So let me do the following two things. So first, I want to write down about what I think is the role of the basic curvature, and well, roughly also of the basic curvature for Courant algebroids in field theory. And then I will do this by means of an example. Actually, the example is about this. We are working on the example about that with Noriaki Keda in the context of the Courant sigma model. So the example I'm going to discuss is the Poisson sigma model versus the twisted Poisson sigma model. Okay, so this is a theory of maps X with components X mu, let's say, from a two-dimensional manifold to a Poisson manifold P, or a twisted Poisson manifold when there is a free form in the game. So this would be well, I would write this because it would be wrong. But so when there is a free form in the game, this is a twisted Poisson manifold in the sense of Severo-Weinstein. When H equals 0, this is an ordinary Poisson manifold, which is the target space of our field theory. Now, moreover, the other field that we have is a one form. So this is a one form on sigma, with values in pullback of the cotangent bundle of the target space. And well, the theory has an axiom, the classical axiom, which is a function of x and a, which is a mu x mu plus 1/2 P mu of X, where P mu are the components of the Poisson structure, A mu, plus potentially a Vesuvian term, which is given by the threefold. Okay, you have to make sure that this is well defined, of course, because this is defined on a membrane, on an extension of the sigma 2 to sigma 3, and you have to be sure that the extension exists and that it doesn't depend on what sigma 3 is. Okay, but so like I'm trying to discuss these two things kind of simultaneously here, right? So the question, let's say, the problem, it's a solved problem, right? It's not a problem, it's a solved problem, but I'm going to say what the problem is. So the problem is to find the BV action, right? So to find the BV action. In other words, the solution to the classical master equation in the BV formalism. And then this, for the Poisson sigma model, this is given by the so-called AKSE construction for QP2 manifolds. But for the twisted Poisson sigma model, it is not given by the AKSE construction. So the AKSE construction, it's like, I'm sure most of you know it. So it's a way to get solutions to the classical master equation for topological field theories. Okay, and a prototype example is the Poisson sigma model. It's maybe the simplest AKSE theory, maybe not. And the point is that when you introduce a twisted Poisson structure as a target space with a three form, the AKSE construction doesn't know how to find the solution really directly. I mean, the vanilla construction doesn't have Vesuvian terms. Now, so of course, this is the answer to this is quite simple. The answer to this is less simple. The solution to the classical master equation is known. It was found by Atiyah and Thomas Strobel in 2019 only, by direct methods without the AKSE construction. They actually showed that naive AKSE construction gives you a wrong solution. It gives you something which is not a solution. But you see, there is an interesting answer to this problem which doesn't go through this. So the problem is, can we put these under the same roof in a way, right? And the answer is, I'm not going to write down the BV action, but I'm going to write down the BV-BRST operator. So the BV-BRST operator for the model is when it acts on the field X, and I'm going to do it in a basis independent way. So this is a row of epsilon. Epsilon is the cost corresponding to the Gates symmetry of the one form. The BV operator on epsilon, let's say on epsilon first, is equal to the E torsion. And the BV operator, I'm going to write only the fields here, not any antifields. On A is the covariant exterior differential on epsilon. Then I think it's minus the E torsion, the epsilon, and then it's minus the E curvature, epsilon, with the antifield of A direct. Now it's really a basis independent way to write things. And this is the BV operator. So the BV operator is controlled by the E torsion and the E curvature. And guess what? I mean, this is valid for both models. With a difference, of course, it cannot be equal in the top two ones, with a difference that in one case, the connection on the manifold is without torsion. In the other case, the connection on the manifold has torsion controlled by the free form H. So it's a different choice of connection to get the BV action of the one and the other model when you write things in this way. And one model doesn't have and the other has AKSE construction, but it doesn't matter. Okay, do I have a few minutes or? Great. So one more thing I want to say then, in the last couple of minutes. I think this is a very interesting story, and of course, I don't have systematics for that. Okay, I have this example, which it's not even. I mean, I didn't do this even myself. Like the answers are no, right? And moreover, I mean, we have done the same thing. For example, for Dirac sigma models, which have target spaces which are Dirac manifolds, and these have no Lucchese construction anyway whatsoever. But again, what you write down is something very similar. It's controlled by these tensors here, by the basic curvature here. You see that the E curvature doesn't appear at all here. And I do think also that, so we are in the process of doing the same thing for the Courant sigma model and for what would be called pre-Courant sigma models, when you have pre-Courant algebroids as targets. But of course, I mean, this is maybe I'm already going to my conclusions, but of course, what screams here is that there should exist some sort of systematic construction, which is not orthogonal to AKSE, but somehow it knows a little bit more that it can treat, for example, Vesuvino terms or even non-topological fields. But okay, let me go first to my last part, which is the role of the Atiyah cocycle. So now I'm going to get a little bit more general. I mean, I could actually continue with the Poisson sigma model and explain to how you should think of the interplay between the model and the Atiyah cocycle. But let me be a little bit more general. So I'm going to work in the context of some work that I've done by Grudzinov and Strobel. And roughly, because I don't have that much time, I'm going to consider like sigma model style theories like this. So I'm going to consider maps from a Q manifold, which I will take it to be the grid shifted tangent bound of the space-time, which like it has functions which are differential forms, of course, to a DG manifold MQ. Okay. And of course, if this is a QP manifold, this would be sort of the ATD construction, but let's be a little bit more general. And of course, the Poisson sigma model fits in this picture too. And then I'm going to consider maybe that I have here some collective coordinates x alpha, and that the fields of my theory, I would denote them as phi alpha, are the pullbacks of these coordinates. Okay, so these are coordinates of different degrees. So in principle, these can be scalar fields, as we had before. One forms A1. So this is what we had in the Poisson sigma model, right? But you can have maybe even two forms. You can have three forms, and whatever. So let's be roughly general. So then, if you assume a rather general structure of what the field strengths of these fields are. So let's say that they are d phi A minus the components of the homological vector field Q, function of phi. And if you assume also that the structure of these transformations for the fields is something reasonable like, well, let me make an answer here. So these are coordinates on sigma and the alpha beta of phi. So let me emphasize though that these are not most general things that we can write. Actually, they kill a lot of interesting theories what they wrote, but like the Poisson sigma model and similar theories are in, and much more general, but not the most general. Then, actually, if you impose the conditions which are like the most reasonable conditions you will impose in Gates theory, that the derivatives of the field strengths are 0 when the field strengths are 0. So this is a general form of a Bianchi identity, right? And secondly, that the transformations of the field strengths, so the field strengths transform covariantly, so they are also 0 when the field strengths are 0. Then you find that the general form of the Gates transformations is, so delta phi alpha is d epsilon alpha plus epsilon beta. And what you find here is that this mu is the derivatives of the homological vector field. When you do the transformation of the field strengths, what you find is some signs which are not so important. Epsilon beta, f gamma, b gamma, b beta throughout the second derivative of models. Now, if you add some deltas and distance here, if you want to make it a little bit better looking, and what you have is that delta phi alpha is of the Derived differential with the pullback, with the extension of the pullback. Actually, I will come back to this with epsilon alpha plus the pullback extension with B1 epsilon alpha, where B1 is the differential of the Courant to infinity algebra that was discussed before. Delta F alpha is equal to minus I star B2 F epsilon alpha, where B2 is the Atiyah cocycle, or the second Courant to infinity bracket. And then actually, if you do commutators of gate symmetries on phi alpha, what you find is that what you get is minus B2 epsilon 1 epsilon 2 here on phi alpha plus B3 F epsilon 1 epsilon 2, where B3 is the third bracket of the Courant to infinity. So there seems to be interesting underlying structure in the general setting of these higher gates theories, which gives rise to this Courant to infinity algebras, whose binary bracket is the Atiyah cocycle. Okay, so that's the role of the Atiyah cocycle and more general of this infinity one algebra in higher gates theory. But I emphasize again that this is not the most general thing that one can write. Stay tuned about more general things. But nevertheless, I think this is fairly general enough to teach us a lesson already. So just to conclude, and there are a lot of interesting stuff that I will be happy to discuss with you. As I said, we are working now on figuring out the full structure of the covariant form of the Courant sigma model in this setting, and also the relation to the Atiyah cocycle. And it would be interesting to find a systematic way to do ATAZ with Vesuvino terms, also ATAZ for non-topological settings. There is an interesting work, for example, by Maxim Grigoriev and Alexei Kotov on this, based on presymplectic structures. I think it's something that is very interesting too. And then, of course, what I would like to do is so one important thing here, one important restriction is that I never allowed these two things here to depend on lower dimensional field strengths. This is actually important. So what one should do is to allow a more general answers here and see what it actually gives you. Well, okay, these are two of the things I'm interested in. And one third thing that I would like to mention is that if you look at higher dimensional models, like because these are more like 2 and 3 dimensional topological field theories. If you try to look at higher ATAZ models, the structures you get are more intricate, of course, and and you know, if you want to be very concise, at least I sometimes like to have very concrete things. So there is a class of topological field theories called twisted R Poisson sigma models that it's a vertical slice in dimensions essentially. So you can write it in n dimension, and it looks like the terms you get in the would-be BRST operator are higher versions of the basic curvature, which was something that was asked before. So actually, this is also something that we are working with Tony Kojoman these days. And I will stop here and thank you very much.
Thanks. Thanks for some questions.
So I would have a question. So you have a QP manifold. How does the structure, the symplectic structure interplay with the cocycle or the Courant and the algebra?
I wouldn't say that the Poisson, the symplectic structure gets really involved in this. What happens though is that if you try to write the analogs of these formulas there, because of course when you have the symplectic structure like in a Courant algebroid, the way that you derive things is using the Poisson bracket, right? So then there is an interplay between the Poisson bracket and the bracket of vector fields. And what you get is that when you try to write down the Gualtieri torsion as torsion on T star 2T1M, you get this term. Well, okay, you have to play with the Poisson bracket additionally here, right? Because of course the fiber metric of the Courant algebroid from this side relates to the Poisson bracket from the other side, right? So because in the Gualtieri torsion you have to contract, you will have the Poisson bracket also here. Now you will get this term, in Poisson brackets with other things, but you will get something more, which is also a tensorial object that I don't know exactly how to interpret, but if somebody has an idea, I would be happy to hear. Maybe this doesn't answer your question, though.
Yeah, and I think that's
Because I don't think that the Atiyah cycle itself sees the symplectic structure.
I was thinking of like if there's a combinable between Q and the Poisson structure, and it was.
Yeah, that's an interesting thing because exactly what appears here is the remainders that you wouldn't expect to have. And it looks something like a compatibility relation between Poisson structure and something. I don't know, but I'm thrilled actually about knowing what this is. I don't know.
Question. Is the procedure which Kera and Strobel apply to find the action somehow generatable, or
the procedure is very, I mean, the procedure is the good old procedure of doing it, right? Because the AKZ construction is a very particular thing, which is a bit too good, right? It tells you that everything is there already in the, like, you know, you take the classical action, you reinterpret it in some way in terms of superfields, and then you get it. But of course, when you want to do that's thrilling, of course. But like when you want to quantize a general theory, you have to apply the good old procedure in general. There's no shortcut, right? The idea would be to try to extend these shortcuts, of course, right? But the method they used is just the ordinary algorithm of doing the BV construction, which works always. It's just painful.
yeah. Maybe another one question concerning the Atiyah cocycle itself. Is it something that comes from some homology theory, or it's an external product of some research, or?
Sure. So of course this is discussed also in this paper and in others. Of course, of course, it's discussed already in older papers by Capranov, for example. But in this particular context, of course, if you take the cohomology of the Atiyah cocycle, this is independent of the connection. And so this defines as a class, right? So there is a cohomology class here. which is the Atiyah class. Which of course it's like it's what the Atiyah was studying in the 50s, 60s, right? About the existence of global holomorphic connections, right? It's kind of similar story.
So in this case, it gives the right answer for constructing this, and the differential in this case is this the derivative. Am I right?
Yes. So essentially, this is like the like you can identify it with the tangent lift of the homological vector field, right? And this is it.
Okay.
Thank you.
So, any other question? Maybe from online participants? If not, we will thank the speaker again.
Thank you.